In the last section in A3, we talked about polynomials and factoring mostly. In section A4, we're going to add on to that idea and move on to rational expressions. So the definition of an irrational expression, it's the quotient of two polynomials in which the denominator is not the zero polynomial. Okay, so we already know what a polynomial is in the previous section. Remember, it's like a constant, a real number plus a real number times x plus a real number times x squared plus a real number times x cubed, dot 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 dot, out to some real number times x to some positive integer power. So what's a rational expression? You take a polynomial and you put it over another polynomial, but the denominator cannot just be zero. Okay, so for example, x squared plus 5x plus 7 over x plus 2. That's a rational expression. All right. So what you can't do is this. Okay, that's not a rational expression because you can't just put 0 down the denominator. Now that's not to say, I mean, you can put something where the denominator could equal 0. If I plug in x equals -7, I do get a 0 in the denominator. That's okay. I mean, it makes that undefined, but that doesn't ruin the definition of rational expression. You just cannot put 0 in the denominator like that. Okay. So just what we learned in the last section about polynomials, a polynomial over a non-zero polynomial is a rational expression. That's all it is. The domain of a rational expression is the set of all real numbers for which the rational expression is defined. So I gave you an example there where I had x plus 7 in the denominator, and when you plug in -7, you get a 0 in the denominator. Remember, you can never, ever, 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 ever divide by 0. That's undefined. Even 0 divided by 0 is undefined. Okay, you can't divide by 0. Okay, so I have to have some examples here. It says, find the domain of each rational expression. So these are the ones in your notes. So this is a polynomial over polynomial. A polynomial over, if you multiplied that out, you'd have a polynomial. And a polynomial over polynomial. And I don't just have the number 0 in the denominator. So they are all rational expressions. Now let's find the domain of each one. Okay, so the domain of a rational expression, it's all real numbers for which the expression is defined. Now, where do we have problems with undefined items? Okay, I just mentioned you can never divide by 0. Okay, and that's the issue here with rational expressions is you can't divide by 0. So let's look at example A here. I'm going to put D for domain here. Right? So what's the domain of this rational expression? The numerator doesn't have anything to do with anything. If I plug any number in for x and take 3 times that number minus 7, you'll get a number in the numerator. From that point of view, you can put anything in the denominator and that number will make sense. But what's the issue here? If I let x be 0, you're going to have 0 in the denominator, which doesn't make any sense. You can't divide by 0. So that's the only issue. It's the denominator that's the problem. So I'm not going to write it fancy like most books do. I'm just going to say x is not equal to 0. Remember, the domain is everything you can plug in and it makes sense. Okay, see, if I plug in 12, I'll have a 12 in the denominator. That's no problem. If I plug in 8.7, I have 8.7 in the denominator. That's no problem. But if x is 0, I have 0 in the denominator. You can't divide by 0. Okay, let's look at B. Domain, D. Okay, now where's the issue here? Again, the numerator is not a problem. 9 times something minus 8, you'll get some number in the numerator. It's okay to get 0 in the numerator as long as you don't also get 0 in the denominator. 0 over 12 is 0. Okay? So it's just the denominator we look at. Well, when is this denominator equal to 0? Notice if x is equal to 3, well, that's 18, but that's 0, and you'll have a 0. So x can't be 3. And notice if x is -15, this factor will be 0. You'll have 0 times something else is 0. So it's everything, it's all x's except -15 and 3. Okay, so the domain is any real number x except for those two. So any other number you plug in the denominator, you will not get 0. Those are the only two values you get 0. Now what about C? Here's a rational expression. Again, what's the domain? Again, numerator doesn't have anything to do with anything here. But look at the denominator. When is that denominator equal to 0? Notice that here it was factored in B, so it was just figure out when each of these is equal to 0. But when is x to the 4th plus 11 equal to 0? Well, let's think about this for a second. If you took your favorite real number and raised it to the fourth power, is there anything you could say about that number? Right? Pick your favorite real number, raise it to the fourth power. That's at least 0. Right? If you take any number, any real number, and square it, it's at least 0. Right? If you add 11 to that, it's going to be at least 11. So notice this denominator is never equal to 0. It's always going to be at least 11. That's because there's a plus here, right? If this were x to the fourth minus 11, it'd be a different story, right? X to the fourth is at least 0. If you add 11 to that, it's at least 11. So this is never equal to 0. The denominator is never equal to 0, so it's all real numbers is the domain. So just because you have a denominator in a rational expression does not mean you're going to have some problem places, okay? Here's an example where the denominator is never equal to 0, so any real number is going to be fine, okay? Now, in general, okay, I'm not just talking about rational expressions. For rational expressions, you just focus on where the denominator is equal to 0. But where else do you have issues with domains, okay? Where else do we have issues with things being undefined? If you take an even root of a negative number, okay, like the square root of -3, the 8th root of -17, those are both undefined in the real numbers. Those are called complex numbers, okay? So, but notice roots don't show up in rational expressions, because remember the powers on the x's are 1, 2, 3, 4, 5, not fractional exponents. Okay. The next example says, perform the division and simplify. Okay, so here we go. So this is a rational expression, right? It's a polynomial in 2 variables, x and y. Okay, in the last section we did polynomials in 1 variable. But it's just the powers on the variables all have to be positive integers, right? So we have a 2 on the x, a 2 on the y, a 2 on the x, 2 on the y, and a 1 on the x, 1 on the y. So these are polynomials in 2 variables. Okay, so it says perform the division and simplify. Well, if you have one fraction divided by another fraction, what was the procedure? How do you divide by a fraction, right? Whatever fraction you're dividing by, you invert and multiply. Take the reciprocal and multiply. So I'm going to go ahead and do that first just to get that out of the way. So I'm changing my division to multiplication, and you have to take the reciprocal. So just to get that out of the way, to divide by a fraction, right, you take the reciprocal of the fraction you're dividing by. Notice I didn't do anything to the first one. Okay, and now we're supposed to simplify. Now, can you do any canceling right now? Okay, sure, I mean, notice you can only cancel when everything's being multiplied and divided. So I have something times something times something times something, the whole thing. You could cancel the 9 and the 18 and get a 2. Okay, now can I cancel the x squares here? Can I cancel the y squares? The answer is no. The x squared is something is being subtracted from the x squared. X squared is being added to something. You cannot cancel the x squares, okay? The x squares are not being multiplied. Now, if the minus y squared weren't there and this whole thing weren't here, sure, you could cancel the x squares. But if you have, x squared plus something and x squared minus, you cannot cancel the x squares here. Well, it seems kind of strange that they would make, well, I made up this problem, that I would make up a problem like this where the only thing that cancels is the 9 and the 18. It says to simplify. Now, hopefully you have noticed that this expression x squared minus y squared is a difference of squares, and we talked about that in the last section. We can factor a difference of squares. Okay? So how do you factor x squared minus y squared? From the last section, that's x plus y, x minus y. I'm not messing with the 9 and the 18 yet. Okay, so I'm trying to factor everything. Now what is this? Now this is a trinomial, it's 3 terms. Now it's in 2 variables, but when I see a trinomial, that makes me think, can I factor with the double bubble? Okay, granted it's a polynomial in 2 variables, but it is a trinomial. Okay, well, factors of x squared, well, that's x and x. Factors of y squared, well, that's y and y. Since these are both pluses, those should be both pluses. Now, check your factoring by remultiplying. So I'm going to FOIL this out. I get x squared. You get xy, and another xy is 2xy and y squared. So it does factor. Okay, now you see what's going on. Now, notice As opposed to here, when I was dividing by something plus something plus something, and here was something minus something. Now, I still have pluses and minuses, but notice it's different now. Right? This is something times something times something divided by something times something times something. When everything's being multiplied and divided like this, you can cancel. Now you can cancel whole terms. I still can't cross this x out with I can't cancel that x with that x because you have something subtracted from it. But the whole thing you could cancel. Okay. So notice I can cancel, say, this x plus y with one x plus y there. So I still have an x minus y. I have the 9, 18 over 9 is 2. And then what do I have left in the denominator? I canceled one of those. I still have an x plus y. And normally we put constants out front. I'll go ahead and do that. Okay? Okay, so let me check myself. 9 goes into 18. Notice 2 is in the numerator because the 18 is in the numerator. I still have my x minus y. One of those cancel, and I'm left with one in the denominator. So there we go. Okay, and you can't cancel an x with an x here because you're subtracting something from it, and you can't cancel the y's either. Okay, that one wasn't too bad. Now the next example you may think is kind of baby-ish, but it's just to kind of refresh your memory. Many students are in such a habit to grab that calculator for everything they've forgotten basic principles of arithmetic that they learned in grade school, or should have learned in grade school. So just as a refresher, I have the example, add 2/3 plus 4/7. Okay, so how do we add fractions? To add fractions, you need a common denominator. And it's easier if you choose the least common denominator. If you don't choose the least, that's fine. It's just then later when you simplify, you could maybe cancel. So just to save yourself some work, it's better if you pick the least common denominator. So we have a 3 and a 7. The least common denominator, least common multiple of those is 21. Okay, so I need to convert 2/3 to something out of 21. I need to convert 4/7 to something out of 21s. All right, so remember the procedure. I want a denominator of 21. Well, what do I need to multiply the 3 by to get 21? I need a 7. But you can't just multiply the denominator by 7 because you want to. That changes the value of your fraction. So you have to multiply by 7 over 7. Because notice that's 1. Right? So that's 2/3 times 1, which is still 2/3. So the value doesn't change. It's just the appearance will change. Now what do we do over here? Again, I want a 21 in the denominator. So I need to multiply the denominator by 3. But again, I can't just multiply the denominator by 3. You also have to multiply the numerator by 3. So notice I have 4/7 times 1, which is still 4/7. So I'm not changing the value of the fraction. I'm just going to change the appearance. Now, how do you multiply fractions? You multiply across. Don't cross multiply. That's something different. Multiply across. So this is 14 over 21 plus multiply across. That's 12 over 21. Should I cancel here? 14 out of 21, I could cancel a 7 in both. I can cancel a 3 in both of these. No, don't do that. You're going to go back to the original problem. Remember, the point wasn't to simplify. The point was to add the fractions. So I have a common denominator, and then how do you add fractions with the same denominator? You leave the denominator alone, and you add the numerators, and I did 26. Okay? So there we go. And we don't do mixed numerals anymore. Don't write, what is that? 1 and 5/21. Okay, we're not in first grade anymore. Don't do that. Okay, so 26 over 21. If you did want to write it as a mixed numeral, you don't write it that way. You would put 1 plus 5 over 21. That's why they should teach in your grade school, because in grade school you write 1 and 5/21. Then when you get into higher order math, you never write that again. So, okay, so that's that problem. So now that we remember how to do that, let's do a problem with variables. 3 plus 1 over a. 3 plus 1 over a. See, when you're in grade school and you just start punching in the calculator and you got your answer, that's all fine and dandy, but then you get to higher level math with variable and the calculator doesn't help you anymore. So that's why you have to know, how to do these things. Okay, so 3 plus 1 over a, I just say add. So let's compute 3 plus 1 over a. Okay, so what you want to do is think of this 3 as 3 over 1. Think of it as a fraction. So now I have two fractions just like I had here. So to add fractions, I need a common denominator. What's the least common denominator, or least common multiple of 1 and a? Well, the smallest number they both go into would be a. So I need a denominator of a. Well, this one already has an a, so I don't have to do any adjusting like I did over here. Leave the 1 over a alone. But I have to do something to the 3 over 1. So what do I have to multiply that 3 over 1 by to get that common denominator? Well, I need an a in the denominator, but then you can't just multiply by a. I have to multiply by a over a. So this is 3 times 1, which is 3. So I'm not changing the value, I'm just going to change the appearance. So this first multiply across, you get 3a over a plus 1 over a. Notice if you do cancel the a's here, which you could do, which you don't want to, but you could, notice you'll get your 3, right? Just like here, if you cancel here, you go back to your 2/3. So you could check yourself to make sure you did it right. If I cancel the a's, I get 3. Now we have our common denominator. How do you add fractions with the common denominator? Well, it's a, so you leave a alone. And you have a 3a plus 1, which is 3a plus 1. You can't combine those, they're not like terms. Right? So we added them together. Could I cancel the a's here? Cancel those and just get 4? No, you can't do that. Why not? Because it's what I said before. The 3a, you're adding something to it. So as soon as you add something to that, you're not just multiplying and dividing. Now if this plus 1 weren't here, yeah, you could cancel. What if the 3 weren't there? A plus 1 over a. Could I cancel the a's? No, because I'm adding something to the a, so you can't cancel. So that's it. Okay, let's do another one. It's a little more complicated. Okay, it says add the following. X over x squared plus 3x plus 2 plus x minus 1 over x squared plus 5x plus 6. Okay, so they want us to add these together. Okay, to add two fractions, we need a common denominator. Now, you could say, well, geez, look at these nasty expressions here in the denominator. They're quadratics, polynomials, because degree 2. You could just say, well, the least common denominator, a common denominator is that times that. You could do that, but that's going to be messy. You're going to have big expressions. Now, see, we really want to take the least common denominator, which is not obvious the way they're written. Right? However, right, this is a trinomial. Why don't we try to factor that? And this is a trinomial. Let's try to factor that. Because if they have a common term, the least common multiple won't be that times that. It won't be as complicated. Okay, well, the factors of x squared are x and x. Factors of 2 is prime, it's 2 and 1. Since these are both pluses, those are gonna, if it factors, they both have to be pluses. Now again, don't do what I just did and just said, okay, that has to be it. No. If it factors, this is what it would have to be, but check by remultiplying. X times x is x squared. You have an x and a 2x, it's 3x, 2 times 1 is 2. So that is correct. Let's do the same thing over here. We have an x squared, so it has to be an x and an x. Now what are the factors of 6? 3 and 2 and 6 and 1. Now, what I was arguing when we factored in the last section, can you get a 5 out of 3 and 2? Yeah, you add them. Can you get a 5 out of 6 and 1? Yeah, you could subtract them, 6 minus 1. But notice here, they're both pluses. So the 6 and the 1 are not going to work because you're going to be adding. So you need to use the 3 and the 2. Now let me check. X squared, 2x plus 3x is 5x, 3 times 2 is 6. Okay, good. Okay, now, to add these two fractions together, I need a common denominator. Now, what's the least common denominator? Well, they both have an x plus 2. So they already share that in common, so we don't have to worry about the x plus 2. But notice this has an x plus 1 and this doesn't. This has an x plus 3 and this one doesn't. So the least common denominator is x plus 2, x plus 1, x plus 3. Okay? So what do we need to do to this first fraction? Right? It's right to add. We need this x plus 3. We need over here. So what do we need to multiply by? Well, we need an x plus 3, but you have to multiply by 1, so I have to put an x plus 3 in the numerator. So it's this fraction times 1, which will still be that fraction. It's just going to look differently. Now, what do I have to do to this one? Right? So this has an x plus 3 and an x plus 2. This one needs an x plus 1. So I need to multiply this by x plus 1 over x plus 1. So notice they will both have an x plus 2, an x plus 1, and an x plus 3. X plus 2, x plus 1, x plus 3. So that'll give us our common denominator. Okay? So let me go and write down the common denominator here. So they have an x plus 2, an x plus 1, and an x plus 3. Right? Now, is it really necessary for me to multiply all that out? No, why waste your time? Plus, the hope is, I mean, once I do the numerators and simplify, it's possible that I may get one of these factors in the numerator and I can cancel. If I multiply that out now, I won't notice, may not recognize that I can cancel something then. So I try to leave things factored as long as I can. Okay, so now we have the numerator. Let me go ahead and write this out. So I have x times x plus 3 plus x minus 1, x plus 1. I could have gone ahead and done that, right, multiplied out, but I'm taking my time. Right? So this times this is the numerator is for this one. That times that's the numerator for that one. Okay, I'm going to make a little room here. Okay. So again, the denominator I'm going to leave alone. Okay, so let me distribute x times x plus 3. That's x squared plus 3x. And now notice this is, this is a minus b, a plus b. That's the formula for the difference of squares. So I know this is going to come out to be x squared minus 1. But if you FOIL it out, you get x squared. You get minus x plus x. That's 0. And then minus 1. So if you combine like terms, I have an x squared plus x squared. That's 2x squared plus 3x minus 1. I usually write polynomials highest power to lowest power. Now, the hope here, I mean, this could be the end. I don't know. Right? Notice in the numerator I have a trinomial. That's why I wrote highest power, x squared, x to the first. This is constants or x to the zeros. But usually don't write x to the 0. I'm hoping the numerator will factor, and then one of the factors will be one of these, and then I can cancel. Now, I don't know if that's true or not. So can I factor 2x squared plus 3x minus 1? So this is going to be scratch work here. This is just do it on scratch paper. Right? So can I factor that? So factors of 2x squared are 2x and x, and I have a 1 and a 1. Now remember, for the minus 1, one of these is a plus and one of these is a minus. Now, is there any way to get a 3x from that? So if I put a plus and a minus here, 2x squared minus 1, so those are fine, but what about 3x? I'll get minus 2x plus x is not 3. What if I switch them and put minus and plus? That's 2x minus x is plus x. No, it doesn't. Okay, so that's the end. Okay? So I tried to factor the numerator, it doesn't factor. All right, but let me explain. Okay, so this is the end of the problem. I want you to be where that's the end. I can't do anything. But suppose my hope was that the numerator factored, and again, I'm just making this up, into something like x plus 2, 2x plus 12, or I don't know, right? And in the denominator, I have the x plus 2, x plus 1, x minus 3. That was my hope, was that the numerator would factor, and I have something times something over something times something times something. Those are the same. Those would cancel. That's what I was hoping would happen, but it didn't. Okay. So if a problem says simplify completely, that's what you would have to try to do. Try to factor that, see if one of those is a factor, then you could cancel. Okay, so another example here with numbers. 5 plus 8. Okay. And I say simplify. Okay, now let's talk about how you could approach this problem. Okay, so I'm doing a problem like this. Again, we're going to do one with variables next. To try to save you some time, I don't know, the books don't really teach you this for some reason. Now, if you wanted to go through the standard procedure, what would you do? In the numerator, get a common denominator of 6, add the fractions together like we've been doing. Get a common denominator in the denominator, add those two terms together. Then you'll have a single fraction divided by a single fraction, invert and multiply, which is a perfectly fine way to do this. There's no problem with that. It's a little tedious and unnecessary. Okay, so when I have fractions in fractions like this, a complex fraction, right? I think of this is just 8, so I think of that as 8 over 1. I try to write everything as a fraction with the denominator. Okay, so I added the 1, so now I have 4 fractions here. So here's what you do. Look at all the denominators in your fractions. 2, 3, 4, and 1. Okay, what's the least common multiple of 2, 3, 4, and 1? Now, you don't have to multiply all the numbers together because that's a common multiple, but it's not the least common multiple. So, 2 times 3 times 4 times 1 is 24. You could use 24, but you're going to wind up having to cancel stuff at the end. What's the least common multiple of 2, 3, and 4? It's not 24, it's 12, right? Since 2 goes into 4, you can just do 4 times 3 is 12, right? So 2 and 3 and 4 and 1 all go into 12, okay? So here's what I'm going to do. Instead of getting a common denominator and add, fraction over fraction, invert, multiply, take the least common multiple of all the denominators, which here is 12, and I'm going to multiply by 12 over 12. Again, I'm multiplying by 1. I'm not changing the value. I'm multiplying by 1. I'm just changing the appearance. So if you do that, all the fractions are wiped out. You don't have fractions and fractions anymore. Now, if you want, think of this as 12 over 1 over 12 over 1, right? So the 12 here is like in the numerator here, and the 12 here is in the numerator. Okay, so let's multiply. What's half? You have to distribute the 12 because there's a plus. What's half of 12? 6. What's 2/3 of 12? Well, that's 24 over 3, which is 8. What's 5/4 of 12? You can say that's 60 over 4, which is 15. Or you can say 4 into 12 is 3 times 5 is 15. Let me do that again, right? Again, pretend that's not there. Multiply fractions at 60 over 4, which is 15. Or 4 into 12, you can cancel 4 into 12 is 3 times 5 is 15. And then here you get 8. You get 8 times 12 over 1, that's 96. Notice all the fractions are gone. I don't have fractions and fractions. And now when you add, you get 14 over what, 111? Look how easy that is. So I didn't have to common denominator add, invert, multiply, right? If you take the least common denominator, right, the least common multiple of all the denominators, multiply by that over itself. If you've chosen the right number, all the fractions, because 2, 3, 4, and 1 all go into 12, all these fractions will turn into integers. And then you just add, 14 and 111. Done, easy. Okay, so when we run into situations like this in class, this is what I'm going to do. I think it takes a lot less effort. Okay, along those same lines then, let's look at the next one. 4 over A minus 3 over B over 1 over AB plus 2 over B squared. And it says simplify. Now I should tell you, if you look at the examples in the textbook, they're not going to do it this way. Okay, they're going to get the common denominator and add, invert, multiply. Okay, on a problem like this, they're going to get a common denominator and subtract, common denominator, add, invert, multiply. Okay. What you may want to do for practice is if you see an example in the text that does what I just said, common denominators, try it the way I just did it and see if you get the same answer they do. Notice I purposely do not do examples from the text itself. I either make them up or I copy ones out of the homework set because I want you to have more examples to look at. So I purposely don't do the examples in the book unless they're just really interesting for some reason. Okay, so let's simplify this. I'm going to do it the way I just talked about here. All four of these are already written as fractions, so I don't have to write as, a over 1. So let's look at all the denominators. A, B, and B squared. What's the least common multiple of all four of those? Now, you don't have to multiply all four together. I mean, that'll get you a multiple, but it's not the least. So what expression do all four of those terms go into? You have to have an A, you have to have a B, but if you have an A and a B, you have your AB, right? So that's just like here. Once you had the 4, you got the 2 for free, okay? But here, B squared. So 1B is not enough, you need a B squared. So I need an A and I need a B squared. So it looks like I need AB squared. So AB squared over AB squared. Now again, if you want to think of that over 1 for each of those, that's fine. Because you got to think of that as in the numerator here and the numerator there. Okay. So again, all four of these have to cancel in the AB squared. Okay. Okay, so let's see what we get. So I'm focusing on the 4 over A. Well, I have 4 over A times AB squared over 1. Notice the A is in the denominator here, the A is in the numerator. A over A is 1, they cancel. So the A's cancel, you're left with 4B squared. Now again, if your denominator doesn't cancel with what you chose there, you didn't choose the right thing, right? All four of the denominators have to cancel. And that minus for here. Now let's do the 3 over B, right? Notice I have 3AB squared in the numerator and a B in the denominator. I can cancel a B with the square, so that gives me 3AB. Okay, now let's come down here. I'm doing the 1 over AB, so this is AB squared over AB. So the A's cancel, I have A over A. B squared over B is just B. And then here, plus, and then I have 2 over B squared. I have 2AB squared over B squared. B squared over B squared is 1. I'm left with 2A. Notice I got rid of the fractions and the fractions in one step. That was the point. Right now, the instructions say simplify. Now, can I do any more simplifying here? I mean, if you could cancel something else, that'd be great. You cannot cancel the B squared and the B because you're subtracting something from the 4B squared. You cannot cancel here. You cannot cancel the A. Okay? Now, even if it was just 2A in the denominator, you cannot cancel the A here because that's being subtracted from something. You can only cancel when it's something times something times something divided by something times something times something. Notice I was able to cancel here. It was something times something times something divided by something. Everything was being multiplied and divided. That's why I could cancel the B. All right. Now you could factor a B out of the numerator, but you can't do anything with it when you factor it out, so that's it. So I think this is a lot easier than common denominator and subtract, common denominator and add, invert and multiply. This is what you would have gotten. It would have taken a lot longer. Okay, so that's section 8.4.